Welcome to this tutorial about advanced modular state machines on Godot 4. I'm going to show you how to make a state machine that is easy to use, scale and read, and that you can reuse on multiple projects and situations. This tutorial is aimed at developers who are already fluent with Godot 4, so I will not be explaining everything I do, especially how animation player works, what is a dictionary and what the button I just clicked does, and so on. First, I want to give a big thanks to Game Endeavor, who created the state machine first. If you haven't, you may want to check out his channel first. What I did was change a few things to make it node based so we can attach it anywhere, and also streamline the action adding new state. And since the initial tutorial was made on Godot 3.5, I just changed it to Godot 4. So let's start with an overview of the base project. I have three scenes, a world, a player and a tile map. I also already have the assets I'm using for prototyping. Link to the creator is in the description. So let's start with the script. I made a script here that is the general script we are going to use and declare as a reusable class. Then for the variable, an already variable that will reference the parent, the ID being that we will then attach the node wherever we need it. The export loaded state variable is an array of string names that simply are all the states our state machine is going to use. Then for the rest, state is the current state, previous state is obviously the previous state, and states is the dictionary we are going to use to actually manipulate our states. Now let's have a look at our ready function. As you can see, we can take all our states and add them in the state dictionary with the function addState. Now you may ask, why aren't we simply using an export dictionary to set our states? And the reason is simple. Dictionaries are painful to set up either programmatically or through an export. With this design, you simply add string names in an array and the ready function does the rest. After that, we call the setState function, pass the first state of the list as an argument, and if you look at what the setState function does, it will take the current state and make it the previous one, and then the past argument and make it the current state. Then it will call the exit state and the enter state after checking that there is actually a previous state or new state to use as arguments. The exit state and enter state function are useful to trigger events when leaving or entering a state, but more on that later. Now we've seen what the ready function does. Let's look at the physics process. First, it will check if we're actually in a state, then call the getTransition function, and if it returns something, it will set the new state with what it fetched, as we've already seen previously when I explained the setState function. The getTransition is a virtual function that we are going to use later on, so bear with me. There's only one function I didn't explain, and it's the stateLogic function. The stateLogic isn't going to be called by the state machine itself, but instead by the parent. I've explained almost everything about the script, however there might be a few gaps in your understanding of the state machine, and that's normal because some of the elements only make sense once you implement them. But simply remember that a state machine allows you to define states, and each state answers three questions. What should we do now? Under what condition should we change state? And what do we do when we actually changing state? And those three main IDs are the stateLogic, getTransition, and enter and exit states. Those are the three components of your modular state machine that you need to remember. Now, I would like to take a moment to visualize what we are actually designing, because right now it may seem very abstract. The two rectangles here represent the parent nodes and the attached state machine. During the physics process, the parent will call the stateLogic function, and within that stateLogic function we will place all the functions that the parent should execute. The state machine will, during the physics process as well, check the transition states by checking various functions from the parent that I nicknamed probes. This may sound very abstract, but for now, it's very important to correctly segregate the logic when you expand the state machine. And again, it will make sense when we actually implement it. Alright, let's dive into it. We are going to implement our state machine. So first of all, we are going to add a node here. We're going to name it state machine. We are going to designate it with its unique name so we can use it later on. Then we are going to put a physics process function and call this one state logic delta. Since we are actually working with our um, player character, I will also call move and slide here. I do it here because I really want to first do the state logic and then move and slide. But there will be scenarios where you can put move and slide inside your state machine. But I'm not going to dive into this right now. Okay, so for the player, we are good. We are going to attach a script to our state machine, and we are going to make it extend our state machine since it's a class we defined earlier. Okay, we created the script. Few things might be important here. First of all, we need the func get ready, and this function get ready is exactly the same as ready. I just call it after the ready function. Why do I do that? Well, it's simple. If I want to use the ready function on a script that I inheriting the state machine class, I don't want to override this. Okay, I always want to keep that. So I just created a get ready function that I can use if I want to call something on the ready function. Then we're going to need a few more functions. So the state logic and the get transition function, and of course the enter state and the exit state. So we are going to implement our first state. So select the state machine and add your first state. So for us it's going to be idle. And now what is the logic here? We are going to put what we do when we are idling here and what we should check to know if we want to change state. So what should we do when we are idling? So we are willing to apply the gravity when we are idling. So we create a simple function apply gravity, and if we are not on the floor, we add the gravity to the velocity.y because it's a character body. Then on the state machine, we want to actually call this function we just created, apply gravity. We want to call it in the state logic. And for that, we are going to do a match statement or a switch statement. So we check the state. If it matches the states.idle in the dictionary, we apply the gravity to the parent. And I believe we should be able to test it out. And it's missing something here. And it works. The gravity is applying. I will slightly lower the gravity in the project settings so you can see better. So let's put it at 100 and let's put the player in the world a little higher here and run the project again. Alright, not bad. Another thing we should do is set up something to monitor the status of this state machine. So we are going to create a little debug tool label like that, and we're going to call it state label. Save it in, well, I have a debug folder, so that's great. And we attach a script here, there, and I paste it here. So we simply attach this node to a state machine, and it will simply tell us in which state we currently are. So let's go back to our player character scene, instantiate this and the state level, and we put it above the player, and we run it again, and we didn't set the targets, of course. State machine, and we're good. And it works, and we can see in which state we are. So I just would like to take a moment to reflect on the the logic and what we're actually coding. So here we have the physics process calling the state machine state logic. Right here, physics process calling the state logic, and the state logic calls the gravity here. It's not written here, but it's what we are doing. So as you can see, state logic, and here apply gravity. And what we are missing now are transition. It's logical because we don't have more than one state now. So we are going to do that right now, and also add sprites and start to add movements. So let's do this. To continue, we need new functions to call inside a character from the state machine, and we need a new variable for that, so I added a speed variable. Then I created a function called apply movement, which I'm not going to detail here, but simply goes either right or left by taking right or left inputs. Also, I map the key for inputs. Then in the state machine, in my state logic, I call the apply movement function because I want to be able to initiate movement when I'm idling. You can say that it works, but we are still not changing state. So I simply select my state machine and add a run state from the inspector. Remember, the get transition function is what triggers state transitions, so we are going to look up for each state what should trigger a transition. I use a match statement and check if it matches the dictionary for idle state. If it does, I then only have to list all conditions that can trigger a state switch. And since the get transition is supposed to return a state, I simply return the state it should transition to. In this case, if the velocity is not equal to 0, the player isn't idle, so we should transition to the run state. Again, remember the logic behind. During the physics process, the state machine will call the getTransition method. If it returns a state, then a transition happens. Now, we want to transition from the run state to the idle state, and the logic is reversed. If the velocity is equal to 0, we transition to the idle state. In the state logic, when we are running, we are still able to apply movements and apply gravity, so we call both functions. We can start to see that the logic is divided in 3 blocks. What we can do in each state and when we transition to where for each state, but one is missing. So that's the next thing we are going to do after we check that the states are correctly transitioning. So let's go to the animation player and create new animation, one for each state. I'm going to key all value needed for the sprite, and then when changing state, the state machine will call each animation. Don't forget to make sure your animation are looping. I simply add a new variable to reference the animation player in the state machine so I can call it easily in the enter state or exit state functions. Then same as before, I simply match the new state we're transitioning to with call to the animation player. So when the new state is idle, I play the idle animation, and when it's run, I play the run animation. Let's run the project and see that it works. We are going to repeat that exactly, but instead add jumping and falling state. Again, create a jump function in the player. Then call the jump function in the state logic inside the state machine. Just remember to call jump only when you are not already jumping, otherwise you are going to infinitely jump. The transition is a bit more tricky since we can start to have 4 states, but if you have trouble following, I'd recommend that you pause and watch what I do or download the final project. The logic is quite simple though. For instance, take the idle state. We are either on the floor or not. If we are on the floor, we should transition to the run state if the velocity.x is not equal to 0. If we are not on the floor, then we check the y velocity to know if we're jumping or falling. Then you should set up transition from other states. For now it's quite simple because those states have rather similar transition and your result should be something like this. When you are done, don't forget the functions you should call in your state logic. We should apply gravity and inputs, but we should not allow to jump when we are either jumping or falling, because that would basically allow us to fly. You then just need to create new animations and call them in the enter state function. And this is the final result for this tutorial. Now I'm going to show you how I've been using this in another project and how the code remains easy to read and very well structured. So if we look at the state machine, we can see that it contains as much as 14 states, but the code looks absolutely clear. We can, for instance, guess that when we're rolling there isn't much we're actually doing, or that we have specific function that we use to do wall jumps and wall grabs. A quick look at how transitions happen show that it doesn't take long to understand how each state is allowed to transition. And that concludes my video, so well, if you have any question, feel free to ask me in the comments, I'll try to answer.